How does the improved stability and Coulomb efficiency of the non-IO2 cathode material lead to a capacity retention of 94% after 20 cycles? And what experimental evidence supports this performance metric? What factors allow about 50% of non-ions to be reversibly intercalated and deintercalated in non-IO2? And how does this reversible behavior influence overall battery performance? How does the synthesis and composition of non-IO2 contribute to its enhanced stability and efficiency compared to other cathode materials? What are the underlying electrochemical mechanisms that enable non-IO2 to maintain high capacity retention over multiple cycles despite its inherent challenges? Can Davis Syringe manufacture solid-state sodium-ion batteries made from seawater in Latvia, turning to O3 type NaVio2 materials? What characterizes the O3 structure when X equals 0 as illustrated in figure 3.13? And how does this structure impact its function as a cathode material in sodium-ion batteries? How does the reversible intercalation and deintercalation of sodium ions in NaVio2 occur within the voltage range of 1.2 to 2.4 V? And what is the significance of observing 3 distinct voltage platforms during this process? In what way does altering the sodium content to form Na2/3VO2 change the material's specific capacity to about 120 mA Hg superscript 1? And what drives the transformation from an O3 type to an O3 type structure during sodium ion intercalation and deintercalation? How does exceeding a sodium deficiency level, with X greater than 0.5 in NaVio2, result in the migration of vanadium ions into lattice vacancies? And why does this migration lead to a pronounced decline in electrode performance? How critical is the rapid reaction of NaVio2 materials with air? And what are the implications of such sensitivity for long-term battery operation? What role does carbon coating applied in a reducing atmosphere play in mitigating air exposure by reducing contact between the NaVio2 material and ambient air? And how does this coating simultaneously enhance the electrical conductivity of the electrode? How do these modifications, namely adjusting the sodium content, controlling the phase structure, and applying carbon coatings collectively improve the cycle stability and rate performance of NaVio2? And what further research might help optimize these interrelated factors for practical sodium-ion battery applications? How does NaVio2 function as a host material for non-ion intercalation and deintercalation? And what role does its lattice transition from O3 type to O3 type play during this process? What are the structural differences between the O3 and O3 phases as illustrated in figure 3.14a? And how do these differences affect ion transport and overall electrochemical behavior? In what way is the chemical composition of NaTO2 similar to that of Na.7TO2? And how does this similarity influence its specific capacity of about 75 mA Hg superscript 1 at an average working voltage of 1 V?